Imagine standing near a massive star, a supernova about to explode. In a single second, it releases more energy than our sun will produce in its entire lifetime. The blast is so powerful that it can erase entire solar systems. And yet, if you were close enough to see it, you wouldn't hear anything. No bang, no roar, just silence, absolute and infinite. Movies lie to us. In space, there are no thundering engines or booming explosions. The real universe is eerily quiet, not because nothing is happening, but because sound simply cannot exist there. To understand why, we have to go back to the basics. What is sound, really? Sound isn't a thing that floats through space. It's not energy moving freely through emptiness. Sound is motion, the vibration of matter. When you speak, your vocal cords push air molecules. Those molecules bump into others, and that chain of collisions travels outward until it reaches someone else's ear. That pattern of pressure changes, those tiny waves in air, is what we call sound. If you like similar educational content, please like, subscribe, and share the video with your friends. But in space, there's almost nothing to bump into. The universe is so empty that the average distance between atoms can be several meters, kilometers, even millions of kilometers apart. And with so few particles around, nothing can vibrate enough to carry sound waves. So even when a star explodes with unimaginable force, even when black holes collide in cataclysmic violence, there's no sound at all. Just light, radiation, and silence. But here's the twist. The silence of space doesn't mean it's lifeless. It's filled with waves, just not the kind our ears can hear. In the next part, we'll explore what kinds of waves actually travel through space, and how scientists have learned to listen to the universe, even in the absence of sound itself. To truly understand why space is silent, we need to be precise about what sound actually is. Not intuitively, but physically. Sound is not an object. It's not energy freely flying through emptiness. Sound is mechanical vibration. When a sound is created, something physically moves. A speaker cone vibrates. Vocal cords vibrate. An explosion pushes nearby particles outward. These particles collide with neighboring particles, passing the motion along like a chain reaction. That moving pattern of compression and expansion is a sound wave. And here's the crucial point. Sound cannot exist without a medium. On Earth, that medium is air. Underwater, it's water. Inside solids, sound travels even faster. But space is fundamentally different. Outer space is an extreme vacuum. Not perfectly empty, but close enough that for sound, it might as well be. The density of particles is so low that there's nothing to transmit continuous vibration. Particles are simply too far apart to pass motion along in a meaningful way. It's like trying to create ripples on the surface of a lake, except instead of water, you have a few droplets scattered kilometers apart. No matter how powerful the event is, sound waves just collapse instantly. That's why rocket engines make no noise once they leave Earth's atmosphere. Asteroid collisions are completely silent, and even the most violent cosmic explosions produce no audible sound. Not because they're weak, but because there is nothing there to carry the vibration. This is where people often get confused. If space is silent, how can we receive signals from it at all? How do we see stars, communicate with spacecraft, or study distant galaxies? The answer is simple, but profound. Sound is not the only kind of wave that exists. In fact, the universe is filled with waves that don't need any medium at all. And those waves are the reason we can still hear the universe, just not with our ears. In the next part, we'll look at electromagnetic waves, light, radio waves, and radiation, and explain why these waves can travel through empty space effortlessly, carrying information across billions of years. At this point, something important becomes clear. Space is silent only when it comes to sound. In every other sense, it is incredibly active. The universe is filled with electromagnetic waves. These waves are completely different from sound. They do not rely on vibrating particles. They don't need air, water, or any physical medium at all. Electromagnetic waves are self-propagating changes in electric and magnetic fields. Once created, they move through empty space entirely on their own, at the speed of light. Visible light is an electromagnetic wave. So are radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. And the universe is constantly producing them. Stars shine because nuclear reactions in their cores emit enormous amounts of electromagnetic radiation. Galaxies glow across the entire spectrum. Pulsars send out rhythmic radio signals. Black holes accelerate particles so violently that they emit intense X-ray and gamma radiation. We don't hear any of this, but we detect it. Telescopes are not just space cameras. They are receivers. Some collect visible light. Others capture radio waves that are millions of times longer than light waves. Some observe X-rays from extreme environments that would instantly destroy any living organism. This is how we study the universe. And here's where it gets really interesting. Scientists often convert these signals into sound, not because they are sound, but because the human brain is incredibly good at recognizing patterns through hearing. This process is called sonification. A pulsar's radio signal can be translated into a steady ticking noise. The rotation of a neutron star can become a rhythmic beat. Data from galaxies can be mapped into rising or falling tones. These sounds are not real in the physical sense, but they are real representations of real cosmic data. So when you hear the sound of a black hole or the music of the universe, you are not listening to space itself. You are listening to information transformed into a form your senses can understand. The universe doesn't speak with sound waves. It speaks with light, radiation, and signals that travel effortlessly through emptiness. But there is still one more kind of wave, stranger and deeper than all the rest. A type of wave that doesn't move through space, but moves space itself. In the next part, we'll explore gravitational waves, ripples in spacetime caused by the most violent events imaginable, and how they allow us to listen to the universe in an entirely new way. So far, we've talked about sound waves and electromagnetic waves. But the universe has one more way of communicating, and it's the strangest one of all: gravitational waves. According to Einstein's theory of general relativity, gravity isn't a force in the traditional sense. It's the curvature of space and time caused by mass and energy. Massive objects like stars, neutron stars, and black holes don't just sit in space. They distort the fabric of space-time itself. And when something extremely violent happens to these objects, space-time doesn't stay still. It ripples. When two black holes spiral toward each other and collide, they don't create a sound wave. There is no air to vibrate. Instead, they send out waves in space-time itself, gravitational waves that travel outward at the speed of light. These waves stretch and compress space as they pass through it. Not metaphorically, literally. When a gravitational wave passes through Earth, it slightly changes the distance between objects. The effect is unbelievably small, smaller than the width of a single atomic nucleus. But it is real, and we can measure it. Gravitational wave detectors use lasers and extremely precise instruments to detect these tiny changes in distance. When space-time stretches in one direction and compresses in another, the detector registers it as a signal. This is how scientists can hear the collision of black holes billions of light years away. Not with ears, not with sound, but with mathematics and measurement. And just like with electromagnetic waves, scientists often convert gravitational wave data into sound. When translated into audible frequencies, a black hole collision produces a short rising chirp. Again, this isn't real sound. It's a representation of a real cosmic event. What's fascinating is that gravitational waves give us information we could never get from light alone. They pass through matter almost untouched. Dust, gas, even entire stars can't block them. That means they carry clean, direct information about the most extreme events in the universe. So even though space is silent, it is far from inactive. It vibrates, not with sound, but with the motion of space-time itself. And now comes a powerful question. If sound cannot exist in space, and if silence is the natural state of the universe, what would happen if space wasn't silent? In the next part, we'll explore a hypothetical universe where sound could travel through space, and why that universe would be far more chaotic, unstable, and dangerous than the one we live in. Let's try a thought experiment. What if space were not silent? What if the universe were filled with a dense medium, gas, plasma, or something else, thick enough to carry sound waves across vast distances? At first, it sounds exciting. You could imagine hearing supernova explosions, the deep roar of stars collapsing, or the constant hum of galaxies moving through space. The universe would feel alive in a very literal, audible way. But from a physical standpoint, this would be a disaster. Sound requires matter, and matter creates resistance. If space were filled with a dense medium, everything moving through it would experience drag. Planets would slowly lose energy. Orbits would decay. Objects would spiral inward instead of remaining stable for billions of years. Entire solar systems would fall apart. Galaxies would not maintain their elegant spiral shapes. Over time, they would collapse, smear out, or lose their structure entirely. The long-term stability that allows stars, planets, and eventually life to exist would be impossible. There's another problem. Sound is a form of energy transfer. If sound could propagate freely through space, then the immense energy released by cosmic events would spread much more aggressively. Supernovae, gamma-ray bursts, and other violent phenomena would disturb vast regions of space, constantly shaking the cosmic environment. Instead of a calm, transparent universe, we would live in a permanently noisy, turbulent one. Silence, in this sense, is not emptiness. It's order. The near vacuum of space allows light to travel enormous distances without being scattered or absorbed. It allows gravitational structures to remain stable over cosmic time. It allows information from the early universe to reach us almost unchanged, billions of years later. The silence of space is one of the reasons we can study it at all. Without it, astronomy as we know it would be impossible. Signals would be distorted, blurred, and drowned in constant interference. The universe would be louder, but far less understandable. And this leads to a deeper realization. The universe is not designed for human senses. It doesn't care what we can hear or see. Its fundamental processes operate on scales and in forms that require instruments, mathematics, and imagination to uncover. Sound is simply not part of that framework. In the final part, we'll bring everything together and answer the core question. If the universe is silent, what does it actually mean when we say we are listening to space? When we say that space is silent, we don't mean that nothing is happening. In fact, the opposite is true. The universe is constantly active, violent, and dynamic. Stars are being born and dying, galaxies are colliding, black holes are merging, and space-time itself is rippling across cosmic distances. What silence really means is this: the universe doesn't communicate in ways our senses evolved to understand. Human hearing is designed for life on Earth. It works in air, over short distances, and within a narrow range of frequencies. The cosmos operates on completely different scales. Its messages are carried by light, radiation, and distortions of space-time, not by vibrating molecules. So when scientists say they are listening to the universe, they are speaking metaphorically. What they are really doing is decoding signals. They collect electromagnetic waves with telescopes, measure tiny changes in space-time with gravitational wave detectors, and translate those measurements into data we can analyze, and sometimes into sound we can interpret. This translation is not a trick. It's a bridge between human perception and cosmic reality. The silence of space is not a flaw. It is one of the reasons the universe is readable at all. Without it, information would be scattered, blurred, and drowned in constant interference. Instead, light from distant galaxies can travel for billions of years, almost unchanged. Gravitational waves can cross the entire universe carrying pristine information about ancient cosmic events. Silence preserves structure. Silence preserves history. Silence allows understanding. So the next time you imagine space as empty and quiet, remember this: it is silent not because it is lifeless, but because it operates on a level deeper than sound. The universe doesn't shout. It doesn't whisper. It reveals, patiently, precisely, and without noise. And the more we learn how to listen without ears, the more clearly we begin to understand where we are, and how extraordinary the silent universe truly is.